This is exciting. I'm really excited to be here at the NDC with all of you. But also, I'm super excited to be the first time in Oslo. I had yesterday with friends of mine a lot of brunost. It's delicious. But of course, you didn't came here to listen to me praise the Norwegian cuisine. You hear about learning what I learned about source generators in Roslyn. So, my name is Stefan Po. I started coding in 2008. I'm originally from Austria. I started my first C# application in 2012. I did Unity back then, so this was Mono. I then switched to .NET in 2013 when I moved to Germany. The Germans, they really taught me how to do .NET and C#. It was an excellent experience. And I learned also all the predecessors to source code generation via Roslyn. For example, D4 templates. Actually didn't do FODI, IL weaving via FODI. However, I did check out PostSharp and also reflection emit and creating expression trees. And source generators are now the latest addition on how you can generate code at compile time, so that it's fast at runtime. In last year, I started actually with Roslyn. The Roslyn API is very exhaustive. I think now I'm now 1.5 years into it, and I believe I know 5%. This is a beast. And doing source generators now, I started this year. Half a year ago, actually, after listening to another talk which inspired me. And source generators are awesome. Currently, I'm in Austria, working as a senior developer at Admiral Sportwetten in Vienna. And I listed here some of my alter egos if you want to connect and tell me about the talk, what was good, what was bad. Maybe you have some questions. I would like to connect. So, what are we going to talk about tonight? So, in C#9 added 2 small features which facilitate Roslyn generators. We will check them out. Then we have a look at the laws of source generation, what to do, what they can do, and what they are not supposed to do. We will check out some examples. .NET 6, the BCL, now actually ships with source generators. Microsoft is building source generators themselves. We will check out the anatomy. How does a source generator look like? What base classes are there, and so on. We will see the tooling, which facilitates us developing these. A bit of debugging. I am prepared. We will see, there is a bit, if you want to enable more up-to-date features, such as nullable reference types. There's a bit of a tweak you have to do there, but we will see how this works. We'll talk about the different versions, since Roslyn generators are ever evolving. .NET 6 just got new features. We will see some performance issues that we will also solve. We'll have a brief look how this looks like in Nuget, so how we can ship our source generators to other developers. And there will be tons of examples and some more resources. So, C#9. In C#9, which shipped with .NET 5, roughly last year, 2 features were added under the title Now Support for Source Generators. Previously, C#8 and lower, you could have partial methods, but they must be returning void. They cannot have explicit visibility. They are always private implicitly. They cannot have out parameters. And for example, if we have a partial method without an implementation, this actually gets stripped out of the code. But now with C#9, those rules got a little bit lifted. So since C# is always so far, very backwards compatible, I here have a partial method, and I'm not calling it in code. We see the IDE tells me this is not used, so this will actually be stripped out. It will not be in the final compilation unless we really use it. And the old rules apply. I cannot return string. This will immediately result in an error. However, if I now state an explicit visibility, perhaps internal, or any visibility, now the new rules apply. And the new rules allow all that was forbidden beforehand, but we must supply an implementation. If there is no implementation, this will cause a compiler error. This will not compile. But I now actually have a source generator in place already, which now fills this whole. So somewhere is code which now has the same definition and actually returns something from this get method. So let's see what happens if I call this. Let's get the string. Let's run the application. And I didn't write any, there is no user code that actually produces now the from generator, but the actual generator is producing it. So it's part of the compilation, but I didn't write it directly. Another thing that got added are module initializers. So there is a new attribute, the module initializer attribute, also available since .NET 5. And we can put the module initializer attribute on a method which is static, somehow visible, so it can't be private nor a local function, must be accessible. It must return void, cannot have any out parameters, can't be generic, can't take any generic type parameters. And this is then picked up by the compiler and called before any other code. So if we have some static initializers, they are called after the module initializer. So we could have a module-wide, which is most likely assembly-wide, initialization at the beginning. So I will briefly get my snippet here. So I have here a text property, and I set it via the module initializer. However, I never call this init method directly. Yet, if I print this property, it says initialized what the module initializer sets. This is called before anything else. And those two help building source generators. Now, what are the laws of source generation with Roslyn? Perhaps let's have a brief look on how this actually looks like. So this picture basically shows it very well. In the beginning, now my shortcut stops working. Sorry for that. In the beginning, there is a compilation which consists entirely of the user code. This then gets shipped or pushed to the source generator, to any source generator which are there. They now basically can run through all the user code. They see all the user code. However, they don't see the syntax trees of package references or other references, but they could access the semantic model behind it. And then the new generator may or may not generate no new source. This is actually strings. This is strings in C#. Then get back to the compilation and are compiled together with the user code. So if our source generator creates a compiler error, the user ends up with a compiler error that they can't actually really fix because it's the source generator generating them. The generated source can be edited by the user. And the laws around that is that we do retrieve the user code, and with that, the syntax trees. So that's all the nodes. For example, a private keyword that's in the huge syntax tree, just a node or a method declaration, and so on. You can also grab the semantic model, which gives more information about the actual type. And we can add new source as strings, and we can only add source. We cannot remove or manipulate source. So this is not really a replacement for example, IL weaving. This is so far the restriction. It could produce diagnostics because it's basically, technically, it's an analyzer. Analyzers can do diagnostics such as reporting infos or warnings or even errors, prevent the compilation from succeeding. And we also may access additional files. Additional files in the compilation are, for example, the app settings.json. Source generators are unordered. They do run in a defined order, but it's not documented what that order is. And so that they cannot depend on each other. The output of one source generator is not visible to the next generator. And yeah, technically they are analyzers. So the two most prominent use cases are either with source generation we could avoid having the user write tedious implementations. For example, iNotify property changed. That's pretty much always looks the same. It's a certain pattern that we apply. Or implementing I equatable. Well, records are now solving that a bit. They are not source generated. They're actually a C# feature, a language feature. And the second use case is we could avoid reflection, so that we can interact with the user code and build upon it. For example, in an ASP.NET Core application, don't find the controllers via reflection, but actually find them at compile time already. So then startup gets much faster. And I also linked the cookbook if you want to check this out. This is like the prime source of how to build source generators. So now let's actually get to it. How does a source generator look like? Now with .NET 6, 2 source generators are shipped. We have in system text JSON and also in logging.abstractions, which saves us writing boilerplate code, but also gives us a lot of performance. So let's go with logging first. I grab this method here. So this is how the generator works. The generator analyzes my code, searches for a partial type, in this case the log type, and searches for a method, a partial method, which has the logger message attribute on it. Now I define my values to this log message. For example, 240 as the event ID. The log level is information, and I can do a format string, which then gets filled in by the parameter. And this method must have a logger in it. If I remove this logger, then I will get a diagnostic. So this diagnostic is now actually from the well, actually, the generator is now not generating something, so we missed that implementation. We need that. It doesn't have to be an extension method. It can be. Now we can call that. Instead of here, let's say log.hello, and we need to pass, actually, it's an extension method, so I can say this, and we can pass NDC Oslo. And there's a bunch of code generated by the generator. I can 12 into this, and this is generated by the source generator. We see at the top, Visual Studio warns us that this file is auto-generated. It looks very similar in wider. There is a lock on top telling you we can't edit it. Doesn't make sense because it's generated. And so this is very similar. We could also do this manually with the logger message.define to have the high performance logging, but it's tedious to always write the same code, so the source generator reduces that. And another use case, is about performance. System text JSON. So this is actually shipped with the .NET 6 BCL. I define here, I define some entity. Now I define another method that gets picked up by the generator. The generator searches for types which have JSON serializable attribute applied, and also are partial, deriving from JSON serializer context. And I don't have any implementation, but it compiles because the JSON serializer context does have an abstract method. I do need to implement this, but it's a generator taking over. And the usage is now such that I define my entity. I say JSON serializer.serialize and use this new generator type. So there's the serializer context. This is my type that I defined down there. .default.entity. And this is now the type information that is used for deserialization, but also serialization. The other way around. First serialization and then the round trip deserialization back to the original entity. And when we run this, we will see first the JSON, then the deserialized record again. We can also control this analyzer via the source, JSON source generator options. We can, for example, I passed in true, I could also pass in false. So now the output string is not intended, now we just have one line. So this is what the analyzer is inspecting. And a lot of code is generated here. If we go to definition, this is all generated by the generator. So this is the most naive, direct code that you could write to serialize an entity. It's no reflection, so it's a lot of code, but it's significantly faster. There is also with .NET 6 ships a source generator with Blazor so that the Razor files get source generated. So let's come to the anatomy of a source generator. If I want to write this myself, not just use the generator from somebody else, we basically, let me quickly check try to restart. Zoom it. No, restart didn't fix it. We basically have to consume the package microsoft.codeanalysis.c#.workspaces. It's not in the system namespace, it's in the Microsoft Code Analysis namespace. This is everything Roslyn starts with Microsoft.codeanalysis. And its source generators are available since the version 3.8. I always like to include the code analysis analyzers, which is an analyzer packages which scans the source generator code that I write and produces warnings if I don't follow the rules. For example, with type equality in Roslyn, rarely any type implements equality via the equals operator, so there are special comparers for that to use. Then we have a type which derives from I source generator. And we need to apply the generator attribute. This is very important, otherwise the tool, for example Visual Studio or the .NET SDK, will not pick it up. Then we have two methods, the initialize and the execute. We will come to that right in a minute. And optionally we can use a syntax receiver, which is basically a visitor which calls on visit syntax node on each and every syntax node that is found. So let's have a look at a source generator. So maybe you have seen the talk from David Fowler about implementation detail matters, where he briefly shows how an enum.toString or the enum.getName and the fastest way how to get the constant string representation of an enum, because there is a reflection and a binary array lookup involved. And a more naive implementation would be to write it ourselves. And this is now what a source generator can do. So it's very naive code. It's basically just switching on this log level enumeration type and going through linearly, doing basically, if it's a type, name of that string. And if we don't find any, we return null so that it's on par with enum.getName. And I did a bit of a benchmark. There it is, and here we see the difference. So at first, we have the generated method, which is 1.6 nanoseconds and has a 0 allocation. And the toString, which involves reflection and a binary array lookup, is 25 nanoseconds and also involves a bit of allocation, which is pretty much the enemy of every high-performance app right now. So how does the generator look like? We have here the type, as we've seen, derives from iSource generator, has the generator attribute on top, and at first there is an initialize method. In the initialize, we now can set up the syntax receiver. So basically, initialize here the syntax receiver. Now the syntax receiver is the iSyntax receiver type, which now visits at each and every syntax node in the compilation. And we basically do this since on visit syntax node is called a lot of times. If I have a small 50 lines of code program, then I have like 500 invocations of this per compilation, which is also per key press. So we need to mind performance here a lot. Don't do any expensive stuff. We see source generators, there is no async method to not invite you to do something slower. This must be fast, otherwise the experience in the tooling would suffer. And so if you have done Roslyn, you will be familiar with the syntax nodes and the expression types. We basically search, and we now search a special method. It has one argument, and it has a special name. So we will search this method and then put it in a list, this invocations list. And this invocations list is then used by the execute method. So the execute method is only run once. We grab the syntax receiver. I also check here if it's actually C#, because I'm producing C# code. This would fail if this would be a Visual Basic project. We get the syntax receiver, and now in this method I get all the symbols, so I can actually get the type behind that enum, so that I can produce, that I know the names of the constants. I also get the options. This is basically some additional files. I can get MS build properties or global analyzer entries, similar to editor config. And then eventually we can generate the source code. I like to use an indented text writer because it nicely supports indentation. So I can create a nice looking C# file so that it's actually readable. I always like to put auto-generated on top, so that automatic tools such as other analyzers or maybe source code coverage shouldn't pick this up. Then it's important to mind compatibility. My source generator could create C#10 code, but if a .NET Standard project, which is per default C# 7.3, would consume it, compilation would fail. We would get all the warnings that this feature is not available in C# 3.8. We must increase the language version. And to enable a more broader consumer range, depends on your scenario, you may want to support multiple or lower languages. I definitely overdid it here. This example is supporting up to C# 2, but find a good balance. You could also say, okay, I don't need the latest features. I just write C# 7.3, since this is a good range. It depends on the scenario. And then basically generate really, this is all C# code, adding up, and eventually, then we will call from this context the add source method. And this is now actually adding the string that we assembled to the compilation. We also pass a hint name. I always add a .g.cs, because this is also a signal that this is generated code, and tools shouldn't pick this up at user code. And then pass it the source text. And then it appears. In Visual Studio, we can actually, so basically we can F12 this. This is also the very same experience in Rider. This enum info that is generated. In Rider, we can also go to the definition, then we see this. And we can also have a look here in the analyzers, in the analyzers tab. We now see all of the analyzers. Generators are analyzers, so they will show up here as well. And we now see that this project has actually 3 analyzers. And if I expand this one, we see this is the enum info.g.cs, which gets emitted. So this is how I can browse the generated code, if there is any. If a generator doesn't generate anything, then there is a little bit of an info saying that this generator doesn't produce anything to the compilation. Also, I want to mention testing. So Microsoft has released a testing package, which is microsoft.codeanalysis.c#.sourcegenerators.testing, and then there is also mstest and NUnit, depends on what you prefer. And we can write unit tests, and they are basically string comparison. Since the compiler is string in, compilation out, we convert this compilation back to a string so that we can nicely compare it. So let me find a smaller test. For example, here, basically have here some usages of the code. It's just a string as input. This is basically what the compiler actually gets as input. And then what I expect to be the output. So I pass in the input code, the expected output code. I can also optionally add diagnostics. And can also, this is not very similar if you have tested diagnostic analyzers. It's very similar with that. So we can say, okay, this should produce this warning and so on at this location. So speaking of analyzers, now I want to show you how we can actually produce a warning. So if I would use this analyzer, this generator, sorry, wrong, for example, actually passing in the log level as an enum type. Since this generator is always also generating this stub. It's always throwing, but it's generated so that we have in the beginning some IntelliSense, so that this method is discoverable. But it shouldn't be called because enum we would need then, now we have no type information, now we would need reflection to actually go to the properties. So this is not fast. And if I would use this now, I should get in the error list. Okay, too many warnings. I was expecting one. Let me quickly rebuild. Okay, sorry about that. We would see one warning, but let me show you the code. So this is how we can define the diagnostic. Diagnostic always has an ID, it has a message, a severity, which is a default severity because the user can change the severity either to a more severe or a less severe via an editor config or a global analyzer setting. And in the code, then we can basically call report diagnostic. So there's the report diagnostic method. Report diagnostic. Yes. So we can also supply the location so that the user knows where this error is, and then we report this this diagnostic, which is very, very similar as we would do with a diagnostic analyzer. I would not like to, I'm not sure, I guess this demo would fail, I'm afraid, I'm not sure what's wrong, but I want to show you the source either way. So we can have, for example, a global config. So this is a file called .globalconfig. If it has another name, we need to set an NSBuild property, but the .globalconfig is picked up automatically. And for example here, it must have the isGlobal is true, and then we can set some strings. So this is a setting that I defined by the generator. The generator is aware of that. I set it to true, which now actually changes the default behavior so that if the constant is not found, we don't return null, but we actually throw. So in this project, where I enabled this, if I go to the same method, we have enominfo.getName. If I have to have this, now it's actually different source code generated. So if we fall through to the default, we don't return null, we actually throw an exception. And then with the return type is not nullable string, this would throw. And the generator can read this via, actually let me search the string. Via the analyzer config options. So we can say, via the generator execution context that we get in the execute method, we can say analyzer config options. We can get the global options, where now this setting is in, and we read it, and we see if the string is true or false, and this can then control the analyzer. Another way how we can control the generator. Another way how we can control the generator could be custom attributes that I apply. Yes. So that's the basic about generators. Now I want to those are the tools. I use them all the time when I do anything with Roslyn. They're super helpful. First off, SharpLab. Well, SharpLab is super for everything. Oops, I wanted to hit. Yes. So usually we can view here the decompiled code, or the lowered code, to be more precise. But we can also change the view to the syntax tree. And now we see the Roslyn representation of our source code. So this here, it's a compilation unit. It has on top, it's called a using directive. This using directive has the node name. Then we have a class declaration. The class declaration has a public keyword as modifier. It also contains one or many method declarations. One of these method declarations now, for example, has the return type predefined type, which is the void keyword. This is how the tree looks like. This is how we can analyze all the syntax nodes and see if you're not sure what I'm searching. For example, if we would like to have every method which returns void, if we want the analyzer cares about that, we could search for each and every method declaration where the return type is the predefined type void. So SharpLab is super handy. Also, Visual Studio has something very similar built in. If we enable it in the installer there is in the SDK you can enable the .NET compiler platform SDK, and then you get the syntax visualizer. And this is pretty much the same as SharpLab does. If I go to any code, sometimes it doesn't display, then you need to edit the source and then it works again. Of course it does not now. Yes, there it is. And here again we see the entire from this source file. One source file is one compilation unit, and we can inspect the tree. And we also see the trivia. Trivia is white spacing and spaces which have more visual meaning than physical meaning. There is also the Roslyn quota. So this is more useful if you would build a code completion. But I can put in any code, public void method. And it's empty. And if I generate, now we get the code that we would need in order to build this tree ourselves. So Roslyn is basically doing something similar, analyzing it, creating the tree. And just as there is source.net, there is source roslyn.io, which is basically the same as the reference source for the .NET, but for Roslyn. For example, we can browse here the source generator. And also, if we go to web access, then actually jump to the source code on GitHub. Where was I? Yes. Debugging, yes, finally. So, Doug is ready. Debugging is now super straightforward, just as any other library, especially in Visual Studio. Visual Studio loads analyzers at startup. So this is what we need to tell Visual Studio and the tooling how to deal with that. So we need the isRoslyn component set to true. We can optionally also emit the generated files and put in a path where to view them. Then we actually see the files generated. But usually the generator does not generate physical files. You will never see those files unless you enable this switch. Then we must define a launch profile with the debug Roslyn component. I think this is available since Visual Studio 16.10, 11, something. I may mix it up. Then target a project that we want to run, so which would actually produce the source for this generator. And we need to include this generator, of course, in the consuming project, and must set the output type to analyzer. And in this case, also the set target framework to .NET Standard 2.0. Roslyn Analyzer and source generators must always be .NET Standard 2.0 because it still needs to work for Visual Studio, which is .NET Framework, so we can't go higher. However, I do multi-targeting here for some benefits, which I will show, so we need to define this here. And when we set this up, we can now actually go to example. We can set now the analyzer, which is actually just a library, a startup project. Now I set a breakpoint. Let's set a breakpoint here and run this. And we'll break now here, and we can inspect. For example, have a look at the pass option, what they are. This is one way of how to enter debugging. What I prefer is debugging from a unit test because it's super precise. I only have the code that I want, and I can have multiple tests. So debugging from a unit test works just as well. Nullable reference types. I mentioned this. A source generator must be .NET Standard 2.0. .NET Standard 2.0, if we have a look at the language versions. Per default, uses C# 7.3. We could set the lang version ourselves to a higher version to have more features. Not all of them will work, especially those which need type support, such as the init keyword. That needs actually the isExternal init type. If it's not available, for example, in .NET Standard the type is not available, it wouldn't work. And features which actually need one-time support. I believe covariant return types need one-time support, so this will never run on anything which implements just .NET Standard 2.0. But still, for nullable reference types, if you want to have these annotations and want to know what is null to avoid null reference exceptions, because they are tougher to debug in an analyzer, in an analyzer and generators, we can multi-target. So actually, multi-target it with .NET Standard 2.0 and .NET Standard .NET 6.0, because the BCL is annotated almost fully annotated with .NET 5, and with .NET 6, I think it's fully annotated. If not, then it's super close. So we have all the nullable annotations everywhere. And if we want to produce a package, it must be .NET Standard 2.0. We can't have multi-targeting with an analyzer. So we will set the, where is it? It's here. So we set the, we only pack, no, wrong line, sorry. Let me break this, yes. So we only pack the .NET Standard 2.0 into the package. And this is the location in the package where an analyzer must be. And now we can actually have, if I go, I definitely have somewhere question mark. No, that's a value type. Where is, for example, yes, here, for example, I actually have a nullable reference type here, and I get these annotations because I'm multi-targeting with .NET 6. But with .NET Standard 2.0 is not aware of this annotation, so we would get warnings. So for .NET Standard 2.0, we have to suppress these warnings, and we can do this with this MS Build property. If it is .NET Standard 2.0, we suppress no warn all the nullable warnings. And we may also want to use this package, since two of the nullable attributes are actually emitted by the compiler, but most of them are not, for example, allow null or disallow null. But we can get them, either we can define them ourselves, or we use this package which introduced them for platforms which do not support them yet. We could also have a source generator creating them. If we have time, I'll show it at the end. Now about versioning. So far we checked out Roslyn 3.8, which is shipped with the .NET SDK, with the first .NET SDK. It's supported by Visual Studio 16.8, and wider supports C# 9 since 2020.3. Now in the next version, 3.9, there was one feature added. I briefly want to show this to you. It's here. So here I now have a 3.9 source generator. And this generator now has a method called register for post initialization. And in this post initialization method, which is here, I can also add a source, but unconditionally. At this time, I don't have the syntax tree available, so I can't really analyze the user code and build something from that. I can only add something unconditionally. For example, a stub method for IntelliSense support. And this now is actually visible to later generator phases. In this generator or the next generator, I have some code down there. We can actually get the compilation, get this type that we produced, post initialization.roslyn3_9. This is exactly the type that we produce up here. And this won't be null, so this is actually available. And the second change is we can have an enhanced context receiver. So this context receiver has the node, just as the other context receiver had, but additionally the semantic model, in case you need in the syntax receiver already the semantic model. But yeah, we should never do too expensive stuff with this in the syntax receiver, because it's called a lot of times. Actually, I'm now going to show you how often this is called. So for this example, I have 50 lines of code roughly. If I go to the output of this 3.9 generator, oops, wrong file, generator, there it is. So we visited actually 386 nodes. And we will also see, I can put this down below, and while I edit, we will see this change. And more nodes get added. So really with almost every key press, this is all executed. And if we would have a big solution, many projects, a lot of source code, so a lot of nodes to put there, or the analyzer would be slow, then my Visual Studio or wider would also slow down, because we need to compile this a lot of code. And this is actually now a performance problem that potentially the 3.8 and above Roslyn generators have. So now with .NET 6, we got an addition. We now have incremental source generators, which are bound to avoid this problem. So here I actually have this project which produces incremental, and this generator does create the isExternal init generator. So for example, let me actually show the example. This should make things clearer. I have here a record, and a record in the emits in the primary constructor. Those are created as init-only properties. But init-only properties require the init keyword, and the init keyword requires the isExternal init type. It must be available. So when I step into this, we see, okay, this type is actually from system.runtime, so it's from the BCL because we're on .NET 6. But if we switch to a lower .NET version, for example, I now switch to .NET Core App 3.1. This was C# 8, and so the init keyword didn't exist, this type didn't exist. Although I have the latest language version, I'm still using C# 10. So records work, but this type isn't there. So we now should actually get a compiler error, but we have a generator in place which creates this. And now we see I stepped into this. This is not the one from the BCL in system.runtime. This is now actually the type that the generator emitted. And this is emitted by an incremental generator. So the programming model with incremental generators are different. There is only an initialize method. This syntax receiver is gone because this was most times the source of performance issues. And we can create the equivalent to the syntax receiver is we can create a syntax provider, which takes two methods. First, a predicate, which is there to filter candidates that we are interested in. And the second one is a transform method where we can transform it to a different type. So if I jump to the predicate, the filter, now this is very similar. We get in the syntax node. This is now again called for every syntax node that we have, but only if there are subsequent. So with incremental source generators, we build a pipeline. And later steps in this pipeline are only executed if a step above actually produces a different output. So if there is a change, then later steps will be executed. If there is no change, the cached output will be reused, so we save work, and the experience in the editor is actually then getting better. Because Microsoft actually had this issue with 3.9 generators and above with the syntax receiver in the big BCL solution. The experience wasn't good because there was so much going on and typing felt sluggish. So they now using incremental source generators in the Roslyn 4.0 version, and this is how the pipeline is built. And once we have created the syntax provider, we get incremental value providers. So this is now the incremental step. So we now define the first step of the pipeline, and now we can do the next step. For example, in our case, now the next step is to combine these types. So what are we actually searching? We are searching for Excellence declaration. So we're searching for record declarations, every record type which actually has a parameter list or has parameters in the parameter list, which means there are definitely properties emitted which require the init only keyword. Or if we explicitly use the init keyword in code, so we find all the accessor declaration syntax, which is basically the thing in brackets at a property, and we search for the init keyword. And those are then filtered out and then transformed. So in our case, we're not really interested in the type itself. We just need to know if it's a rare, so our transform doesn't really do anything. But we could here return something else as well. Maybe we would need an int, so the pipeline now gets an int passed further down the later steps. And now we have those syntax nodes, and we can now collect them. So this will now actually run this pipeline step and combine it with the compilation provider, because we also require the compilation to check if this type is already there. So we can ask the compilation, hey, is there already external init type? Because if there isn't, I need to create it. If there is, I would create a duplicate of the same namespace, and this would cause a warning. So we can check here, do we actually have this type in the compilation? And if we have not, then we actually add the source. And with these pipelines, we can really build very complex pipelines. So this context has many switches. So we can get the compilation, we can get the parse options. The parse options, for example, contain which language version this project was built in. We can get additional texts, such as app settings, or some text file. If I add a compilation to a text file, we could build a transpiler, so I can just pass in, let's say, Visual Basic code as a text file in additional code, and then produce C# code out of that. Or, yeah, this is how we could build transpilers. Again, the analyzer config options that we can use to read from the global analyzers, or also MS build properties, it's also possible. And metadata references there as well. So this is all accessible via the previous generators as well, but now we have this more pipeline-y syntax. And if you have a look at this incremental values provider, they have link-like extensions. There's a select aware method where we can apply more filters or transforms to this pipeline, but it isn't link actually. It's a separate extensions type. It's just link-like. And with incremental source generators, we can now speed up the performance. Actually, if we do only a single compile via .NET Build, then the experience is then there is not really a difference. But if we edit live in for example, Visual Studio, which compiles all the time when we type, this could speed up the experience. And yeah, so those incremental source generators, they are available since Roslyn 4.0. What we need to be careful, they are only supported in .NET 6 SDK. So if I would have a generator which requires Roslyn 4, but would be consumed from a project which uses the .NET 5 SDK, it wouldn't work. The generator wouldn't work because those types are unknown. So again, we need to find a bit of a balance. We could say that, well, I think that the .NET SDK pretty much goes, I think in May, out of support. So maybe go to the newest immediately, if you require the performance boost. Yes, we talked about performance. One thing I will show is how does this look like in Nuget. So we will have we can open this here in the Nuget Package Explorer. So a Nuget package is basically just a zip file in a specific format. And we see this is the folder structure. It must be here. It must be in analyzers, .NET CS for C#, and there lies our analyzer. Oh, yes. And we also want to set development dependencies to true for this package, so that per default we get the private assets tag, so that we don't want our analyzers or our generators in that case to transitively, so that the consumer is transitively depending on those. We went through plenty of examples. I listed here, if you're interested, the slides is all online. The awesome Roslyn has like a bunch of generators. For example, there's also the community toolkit, which has a iNotify property changed generator. It's somewhere in here. So we don't need to manually implement our iNotify property changed all the time. If you would like to know more, I listed here some videos of other speakers about source generators and also some links. I would like to highlight this one since it connects a little bit to the keynote. There is an article about supply chain attacks, how source generators could be used maliciously. Now, if we would have a malicious Nuget package, it can only, under air quotes, only one bad code, but a generator could analyze my source code, so it has full access to the user source code, maybe extract secrets or something else from there, which may not be actually emitted to the compilation because it's additional files which I ignored. So this also opens more, yeah, it's a bit of a danger. So just as with any Nuget package, we should only consume trusted sources. And with that, I would like to know if I have opened up some questions or left some questions unanswered.
Are there any reasons not to always use the incremental generator, or feels like it's just a more performant version, or did I misunderstand?
If we should, if I understand correctly, if we actually should only use the incremental source generator and not the regular source generator, I found it more easy. I find the regular generators more easy to understand. I still haven't fully understood the source, the incremental source generators. They're really new. So perhaps as a starting point, the regular the 3.8 or 3.9 source generators may be a little bit more easier. And when you understand the model and the system, then for a production project, which may be consumed in a big project, then incremental source generators would be the way to go. When you can safely assume that everybody who wants to consume this will have the .NET 6 SDK. Yes.
You mentioned parsing external text files. Used to be .NET as an example, but you can parse anything, I suppose. How do you set up the syntax parsing for that?
So how could we analyze in our generator any text file and have it produce to the code? So we could. Let me jump to the. So I just add any file. Also, I of course want to make it a text file. We need to make it part of the compilation. Just only the .NET SDK per default picks up C# files. We need to make the compiler aware of it. So I'm actually not entirely sure now. I believe it's is it content? I believe it's content. Okay, not entirely sure, but we need to set some build action so that it gets picked up. And then it would appear, for example, now in the incremental source generator, it would appear in the additional texts provider. So, and for the additional texts provider, we basically have source texts. So with C# code, we get syntax nodes. But with regular text, we get a source text. And this is basically a wrapper around a string. So this is how we can access a string with more information. And then we can basically pass this string manually and produce whatever C# code that we like.
There's no embedded functionality for generating syntax tree parsing.
No, so not. No, you have to build it yourself. But you could build your own transpiler. No, there's. I believe there is in one of the repo. I'm sure that somebody already built some out of some specific text format a C# source generator, but I'm currently not aware of some. But there is no built-in. There is nothing there already. Only with C# you get this get the syntax nodes. Do I miss another question or yes?
What are the use cases?
Which use cases? So when I have implementations, when I know in advance what the implementation would look like, then a source generator I could automate this via source generator, so I didn't need to manually implement it all the time, which is error prone. Or if I have some code with reflection, I cannot eliminate every reflection code, but it's definitely subject to maybe replaceable by a source generator. For example, I could, if I build my own CLI command library, which searches for types of a certain command type, usually we'll do this via reflection, find all those types in the assembly which are deriving from that type or are assignable to this type. But with a source generator, we could analyze it at compile time and then directly link it up in source, so we don't need the reflection part. So, okay, compilation now is a little bit slower, but runtime is significantly faster. Did I answer the question? If not, then perhaps we can talk later or via Twitter. And I believe we are on time. So I want to thank you everybody for coming. I hope you learned. I was able to share my knowledges. Tusen Dank. And thank you for staying a while and listening. Have a great conference.